Hi, everybody. Welcome to my talk, or to our talk. We're doing a joint talk together today about powering real-time applications with a modernized cache. My name is Peter Caillot. I'm with Redis now for 8 years, and I lead the product management team responsible for the core engine of Redis. But before we start, I wanted to ask, who knows what Redis is? Can you put it? Oh, almost literally everybody. So I was going to explain what it is, so I'll give you very, very brief what Redis is. So sorry about that. Thank you. Redis is an in-memory data structure store that is most often used as a cache, as a session store, as a message broker, as a database, as a vector search store, or full-text search store. We have nowadays about 2.25 million Docker pools per day, and we actually just crossed 10 billion Docker pools, which is amazing, on the open source version of Redis. We're voted, again, by Stack Overflow as the most loved non-relational database by the developer community. Within my team, we focus upon 3 things. We're focusing on the core Redis open source, and the data structures that you've all been using. We focus upon developer experience, which means client libraries, visual developer tools, Copilot, Redis Insight. Maybe some of you have used it. I see some people nodding. And we also focus upon moving data into Redis and make it easy for you to move data into Redis. I'll talk about that later on. The way I structured the talk is a talk of an evolution. I think everything that we did in the product is a consequence of how users were using Redis. It's not, most often it's users that were pushing the boundaries of Redis, that were hitting limitations of what it could do, and we try to find a better solution for that. Of course, there will still be some product announcements in there, so sometimes there will be like a QR code, which you can use to scan and look into the product later on if you would love to. Because the talk is low on AI, I've asked ChatGPT to create some images. They're quite funny, so I hope it's a bit entertaining. So at least I can say AI as many times as all the other talks that were going on today. And then lastly, later on I'll be joined by Ebre Scacchetti, which I just learned is an Italian last name, who's a machine learning engineer at iFood. And he will talk you through how some of the capabilities that I will show you in Redis, how they're using that at iFood. But I want to start with the opportunity of Redis. According to Microsoft, 80% of the OLTP workloads on Microsoft SQL Server are pure read queries. Oracle claims that for typical OLTP workloads, it ranges between 70 and 90%. And 90% means that for every write you make into a relational database, on average you read the same unchanged data 9 times. Or in other words, if you order food on iFood, you check on average on your phone 9 times that the food is going to arrive. Right? These reads are expensive as they run on relational databases that require lots of compute requirements. And this is exactly why Redis was created by Salvatore. It's about 16 years ago. And it was created to accelerate applications. As a side effect, however, some users, they thought they could also reduce the cost of that relational database. And we'll come back to that later on. This is the first ChatGPT-generated image. Not my favorite. There's one that comes later on. But, so the prompt here is very, very straightforward. So it's a common known problem. The hotkeys is a common known problem in Redis. Everybody knows what it is? So hotkeys happen when keys are accessed very frequently or written into very frequently. Now, there are more than these 2 use cases that I explained here on the slide that can happen, but let's focus on those 2 today. Redis, when Salvatore created Redis, he was thinking about throwing away as many other things in relational databases that were not needed, and he wanted to make it very simple. So Redis has a main thread where all the commands are executed sequentially. And by minimizing, for example, the time complexity of all these operations, and by being obsessed about that, you can actually do many, many operations on a single thread. Now, if you want to scale it, if you want to scale your Redis cluster, you can have a key space. You can actually create a Redis cluster, so you can have many nodes within a cluster. But a single key can only reside in a single shard. You can do some replication, etc., but still there are some limitations of what you can do. There are 2 common patterns here. One is the frequently accessed keys, which could be, for example, in case of a social media, there is an influencer, not me, whose profile is being accessed very frequently. So that could be a hotkey. that is where a high throughput is going to go into a single Redis process. But what we saw when we look into our data in the cloud, how Redis is being used, we actually saw that there was like lots of usage of sets and sorted sets. And we thought like, well, why is that? Like, which use cases are they being using that for? And I don't know if some of the users here are using Spring Data Redis. In Spring Data Redis, you can add simple annotations that say indexed or add index on top of some of the fields you do. And then actually that's translating that into sets and sorted sets. So it's creating secondary indexing use cases in Redis. And what happened then is that if you want to do, for example, you want to say this field and that field, it will do an intersection in between those two sets. Right? But it also becomes like a heavily hotkey in your key space. And hotkeys, the last thing about that is actually that it makes your key space imbalanced. Now, I've been working upon these two problems. And the first problem, like the influencer problem, we've created for that client-side caching. And with client-side caching, we'll actually keep a copy of the hotkey within the client library, within the client application. So on a repeated consecutive read, you will just access the data locally from local memory and avoiding the network round trip. And this is, of course, heavy for great read-heavy workloads. We have some customers that sometimes do one write and read the same key 50 times. That's a perfect sweet spot use case for that. Redis will track each client library, for each client, which keys are being cached in a local cache. And then we can, when there's a write in the Redis database, we can actually send an invalidation to those client libraries. It's been around for a while, but it was not supported by any of the client libraries. So we added the support within all the major client libraries, and it's available since Redis 7.4 onwards. So this solves the influencer problem. For the secondary indexing, we created something that initially was called Redis Search, but we now call the Redis Query Engine. And with the Redis Query Engine, you can define a schema, and the schema defines which field in either hashes or JSON we will index, given also a prefix. The index doesn't reside in the key space, and whenever you do a write into the hash or into the JSON, we will just atomically update the index. And then you can access that index. Now, it comes with a coordinator, so whenever you make a query, a read query, you will hit one of the charts, I say charts, but the nodes in your cluster, and the coordinator will do a map reduce operation to all the Redis processes and will gather the results back. And we've got support for different field types, tags for full text search, tag for numeric, for exact matching, numeric, geo, and also vector. And you can combine in the query, you can actually combine the different fields that you've indexed within an index to create complex queries. Now, this actually changes this is a significant element in cache modernization because it unlocks like a huge variety of new use cases that you can do. One of them could be, for example, common use case is a session store. You put stuff items in your shopping baskets, but the shopping basket is a single hash for all your users. But now you can ask a question like, how many users have this particular item in their shopping basket right now? This is something you can now ask to Redis. Just giving it as an example, but there are many more. One thing is that Redis is commonly being used for is a feature store, an online feature store where you retrieve features to serve them to an AI and machine learning model. We'll talk about later on more. But now with this query engine, you can actually do the selection of those queries. So imagine you're a food delivery company, and you would like to retrieve all the restaurants that are in a specific radius from a specific geopoint. You want to say all the restaurants that are having a tag for example, Italian restaurants. And you want to retrieve all these restaurants and feed them into a recommendation engine. Before that, you had to do like a two-phase approach with some other solution. Now you can do that in Redis directly. And this makes sense because you probably want to serve those recommendations very fast and retrieve them from Redis. The Redis Query Engine is also powering our vector search technology. It enables you to do like blazing fast vector similarity search. And just for you to know how fast it is, we actually have a benchmark. There is a blog post that we have written about that, and you can also find the code that we use for benchmarking this on GitHub. We tried all permutations. We tried different data sets, different embedding models, different vector sizes, different workloads, different queries. Whatever we tried, compared to our competitors, we came out faster. We serve the vectors from memory, so that's the obvious reason why we can do that. One of those use cases that you might be using this vector search technology is RAG, and Aber will talk about that later on. But it also powers a new product that we've been building, which is called Langcache. And again, it's kind of like a sweet spot use case for Redis. It's called semantic caching. So semantic caching allows you to cache responses from an LLM, and then on subsequent similar or semantically similar questions, you can return the response rather than calling your LLM. And as such, you can, of course, increase the performance or the latency to your application up to 15 times, but you can also reduce the cost. You can avoid calling the expensive LLM. We've got a solution there that is served from our cloud. It has a REST API that you can call, and you can also use several embedding models. We have support for OpenAI and Anthropic. We also have our own model that is specifically fine-tuned for semantic caching. Azurion is one of our customers that is using semantic caching, and they were able to do a cache hit rate of 70%. And with that, they would actually reduce the response time in their customer service portal in half. They would cut that in half, and they would get 4 times more engagement on their customer service portal. I personally think that this is a great use case, a technology fit for Redis, right? Redis was used for caching. You can put a time to live on top of this response, so you can recalculate it after a specific time. This is a sweet spot use case. So it's now available in public preview. If you want to get access to it, it's actually, you can directly get access on redis.io/langcache. You can get started with the free database. I'll see the phone coming up, so I'll leave that on for a while. I'm going to switch gears and talk a bit more about caching. So there are several known caching patterns. You've all heard about cache aside, write behind, read through, and all these caching patterns. But the cache aside is like the most common one. So in a cache aside, I know you all know Redis, but I'll still explain it. You first go to Redis when there's a read. You check in Redis. It's not there. You've got a cache miss. You will go to your relational database, execute the query, put it in Redis, return to your application. On a consecutive read, there will be a cache hit, and you will return a point faster. And as such, you accelerate your application. So this is great when part of your data set is hot. Higher P95 latencies are allowed because in some cases you will still have to go to that relational database, and data is changing slowly. And notice that your relational database is serving all the writes, or your primary database, but it's still serving some of the reads, right? Remember that total cost of ownership note that I made in the beginning that Redis was supposed to kind of like reduce the total cost of ownership, and this is not really true because you still need to serve the reads from that relational database. A common problem with this, I love this one. There is still a better one, hang on. So a common problem with the cache aside is stale data. And stale data can occur, of course, when you did a write in that relational database and you've put some keys in your cache. So then at that moment in time, they're out of sync. So the way you can solve that in Redis is by putting a time to live on that key. And it will expire after a certain time, and then of course there will be a cache miss, and you will call that data again. You will call your primary database again. The problem with this is that it's a bit of a guesswork. If you put your time to live very fine-grained, you will have lots of cache misses. And what was the point of having your cache in the first place? If you put it too long, you will get cumbersome customer experience. Imagine, for example, you would put all your order list or your recently bought orders into a cache. As a customer, I buy something, I go and check the order list. It's not there, I buy it again. That's quite a cumbersome experience. So that might not be an ideal fit. Now, this is my favorite. Another problem with a cache aside is, anybody wants to guess what the image on the left is? It's a thundering herd, which ChatGPT took very literally. So a thundering herd problem can occur when, in a distributed system, due to some situation, all requests will go into a single resource, and as such you will overload that single resource. It can happen in our social media, in the influencer, when we put an expiry on the social media and the key will expire. All requests into Redis will be cache misses. They will go to your relational database. It can also happen when you put like a TTL, like expire at a specific moment in time. All the keys with that specific moment in time, they will expire and they will go there. It can also occur as a cold start, because if you start with a cache aside, initially the cache is empty and all your requests will go to your relational database. So the source database still needs to be sized according to serving all the potential reads from that database. Now, this is a quote from a seasoned developer. It helped me great in this talk. right? So Phil Carlton used to work on Netscape over a decade ago. And he stated that there are only two hard things in computer science, cache invalidation and naming things. Now that LLMs are basically writing our codes, we can consider the naming things solved. So if Redis could solve the cache invalidation problem, then we basically solved all the computer science problems. So why is cache invalidation complex? The first reason is that Redis is a non-transactional database, so you don't have the concept of doing something like a two-phase commit in between your writes into those two data source. But that's not the biggest problem. The problem is that the application doesn't know which data points are actually being cached within Redis. You might have a single row and a specific column that resulted into 20 keys, cache keys in Redis. So there's no mapping in between that. The way we see our customers solving this is by using, instead of a cache aside, they use a refresh ahead cache, or a prefetch cache is also a common name for that. So in that case, you move the data from your primary data store into Redis. There's some magic there happening on in the middle. And then you do have some way to capture all the new changes in that database and to replicate them to Redis. In this case, all your writes go into Redis, and all your reads are being served from, all your writes go into your private database, and all your reads are being served from Redis. You could also see this for the architects or the computer science room as CQRS. It's a common use case of CQRS, where you will model your data for writes in a specific domain-specific model, and then you will serve or translate your data into Redis data structures to serving your reads faster. Of course, this is great when data is accessed randomly. You can't have high P95 latencies. Data is in flux, or higher data consistency is required. Now, the way we see our customers doing that is there are three different ways. One of our customers is actually, they have like thousands of cron jobs that move data from Oracle towards Redis. It's literally an operational nightmare. Other ways could be by using complex architectures, using Kafka, moving data, but of course it adds more components in your architecture. Of course, ETL tools could be handy to do that as well. They can do change data capture, but ETL tools are typically made for relational-to-relational workloads, and they don't know about the variety of data structures that we have in Redis. And for that, we created Redis Data Integration. Redis, or short, RDI, it makes it synchronizing Redis from any relational database and soon like any data source. Very straightforward, simple, and fast. And we've built RDI on proven technologies, so we're using Apache Flink and Debezium under the hood. And we're adding our expertise on top of that on how to transform data from a relation or any data source towards the variety of data structures in Redis. So RDI actually is a low-code solution. You can upload a transformation logic towards RDI. It can allow you to do some denormalization. What happens here is that we will we will capture the changes from our initial load from your data source via a CDC collector. We'll have an intermediate Redis database. We're using Redis streams for that. And then there's a second process, which is asynchronously retrieving those items from those streams, is applying your transformation logic, and then writing it into Redis. In that transformation logic, we might also do lookups into Redis, for example, for denormalization. We've got many customers using RDI already on-premise, but Axis Bank is one of those that is actually using it for their mobile banking application. They were originally doing all their core banking logic and writing it into Oracle, and then their mobile banking app was actually serving their reads directly from the same Oracle database. They have 6 million daily active mobile banking users. They were trying to scale, of course, the reads as an application modernization. They were adding Oracle reads replicas, but it didn't hit the throughput that they needed. So what we did is we added RDI, and together with our Redis Query Engine that I spoke before, and now the results speak for themselves, right? Before they had like 173 milliseconds response time at peak time, and now it's 29 milliseconds. They maxed out at 500 requests per second that they could do on their original Oracle database, and now they can do tens of thousands, and they can actually just scale Redis by adding more nodes into the cluster. So I have a demo for that. I did do the recording, so I didn't know I could do a live demo, but in this demo, it's a recording. I will show you some data in a Postgres database. we'll spin up RDI in Redis Cloud, and we'll show you how it results into Redis. And then afterwards, we'll make a change, of course, and hope that the change ends up in being in Redis. So let's go ahead. So I'm connected to the Postgres database. I'm going to show you the tables that are there. It's the Chinook data set. I'm going to show you one table, the genre table. So there are 2 columns. There is genre ID and name, and the first ID is rock, which we'll use later on in the talk. So I've already created like a database, and I will go ahead and connect to that database. So this is Redis Insight, the visual developer tool for Redis. You can see there is no data there, but it's a live recording. So I do ping and pong, and Redis is always friendly and answers me. There's a data pipeline section. I already set up the initial setup there with private link. I can go ahead. I can select some tables. I will do artist, album, genre. And right now in the UI, I can only choose to write into hash or in JSON, but you can write in all data structures, and you can also upload your transformation file. It gives me a summary, and then I can go ahead and I can deploy the pipeline. So we made RDI like secure from the ground up. So this will run in your dedicated environment, your dedicated RDI cluster, together with your dedicated database. What it first will do, now we deploy this, it will do the initial sync, or like hydration. So it will retrieve all the data from the Postgres database. It's not that much, but the time it takes mostly here is to deploy this pipeline, actually. So there we go. Now it transferred those records. There are 647 records in total. And afterwards, once it finalized that, it will go into streaming mode. So we got a notification. It's now in streaming mode, so now it's capturing all the changes from that database. We can go ahead and look again into Redis Insight. The tables are now there. We got genre ID 1. Okay, there's our key rock that is there. So that doesn't prove still that we can do change data capture and we can keep on your cache fresh with, this, with any change that comes. So we'll now do an update in the Postgres database. And for that, we're going to then use, of course, the Bezium uses to write the headlog from Postgres. So instead of showing you within Redis Insight again what the changed value would be, I thought to be creative, and I used our Redis MCP server just to talk a bit about AI and access the data within Redis. So I first asked it, of course, how many keys there are within the database, and it knows there's a tool, DB size. Okay, we got 647 records. So far, so good. Now, then I was doing this recording, and I really struggled typing the right question. I wanted to ask it, like, hey, can you retrieve this genre ID with ID 1? And can you tell me what the value is? But I was struggling a bit. But I thought, like, do I do another recording, or I just leave it as is? Because it's actually interesting. It still figures out correctly what the value is. So the first thing it will do, like, well, I don't know. It's a key value store. It's schemaless Redis. How do I know which key I need to retrieve? So it does a bit of scanning. It's going to scan a couple of keys, and in those scans, you can actually see that it figures out what genres. And with that, it can figure out what is the key pattern you use. Like in Redis, you typically do use a colon in the middle, like to separate specific fields within a key, or to make a hierarchy, or like a nesting, like a tree view. So it figured out, okay, there's what the structure is. It figured out there are 25 keys. Great, and this is the structure, so that's the key that is there. And asked me friendly, of course, if I can retrieve it. And it still doesn't know which command to execute, because it could be a hash, it could be whatever it is. So it first is going to figure out the type, and then retrieve that from Redis. I hope we're going to see rock and roll in the end. I know we will. So there we go. I'm happy to say we're working upon that in our team, that Redis Data Integration is now in public preview. You can go ahead and get access to it by scanning this QR code, or just go to redis.io/data integration. For those who've been paying attention, they might have thought, like, well, in a cache side, I have like a portion of my data set, like 20%. But with this new Redis Data Integration, you will move all my data. And we got a couple of sales reps in the audience. They will be very happy about that. Because it might be that you think that it's going to cost me a lot more. So we thought about that. And when Salvatore created Redis, like the bandwidth of memory was about 10,000 megabytes per second. And nowadays, NVMe storage is 16,000 megabytes per second. Like, so that it's the architectural principles, design principles that he used for creating Redis like 15, 16 years ago, they're no longer valid. So what we created is we created Redis Flex. And Redis Flex is auto-tiering for higher scale and lower cost. So you extend your key space with a slower storage, either SSD or NVMe. And so key and values, they either reside in memory or they reside on the slower storage. Of course, we will keep the keys that you access more frequently into RAM, and the ones that are cold values, cold keys and cold values, we'll keep them on the slower storage. So within Redis Cloud, you can actually choose how much RAM you will have within your database. You can configure that to 90% to be on disk. You can create databases up to 50 terabytes. It starts at 250 gigabytes minimum. And of course, the new pricing is in place, and it reduces the cost compared to an in-memory days by up to 75%. We've got customers like iFood. Abra will talk about that later on. Of course, using this as well. And the top use case for using this is actually a feature store use case. And if you combine it again with RDI, we can actually move and keep that feature store always in sync, the latest feature that you have in your primary databases. One more QR code. Oh, there's one more coming. Redis Flex is, since this week, actually generally available on Redis Cloud. So one more evolution story is that as users were leveraging Redis, they were actually using it for more rich use cases. And this is a beautiful prompt as well, by the way. But what we saw is that lots of users, they were actually serializing Java objects and writing them into strings in the strings data structure. Now that's interesting because what they needed was they needed some level of nesting. They needed like a hierarchical data structure, but the only hierarchical data structure available in Redis is a hash, where you have like one level of nesting. So the prompt here was draw me an image of a JSON serialized into a string. There are many things wrong there, but so what is the problem with that we see that our users, our community actually doing with this is that they would like to do, for example, a small update within a nested document. But to do that, they have to retrieve the entire serialized object, deserialize it, make an update, serialize it, and write it back. Meanwhile, somebody else or some other client might have updated that key, so you need to watch that key, and you might need to retry that entire operation. Another problem is that if you would like to retrieve subpart of your nested document, you still have to retrieve the entire document. And that's not the Redis way. The Redis way is about simplicity and about performance, right? You only want to retrieve and send over the network exactly what you need. So we created a native JSON data structure. There's lots of text on there, but the main point is that under the hood, it's a binary tree. And as such, with JSON path, you can actually do two things. There are many things you can do, but the two important ones to take away from it is that you can do atomic updates on a subpath of your document. So for example, you can say in this JSON, there's a MacBook with a quantity of 15. You can do JSON.increBy. You can specify the path of your document, and you say incremented by 3. This is the Redis way, right? Rather than having to retrieve that document client-side, make the change, and write it back. And you can, of course, also still retrieve subparts of that document. Now, we've built this Redis Query Engine, and this also works, of course, with our Redis Query Engine. So that makes it very interesting because we can now index fields based upon this JSON path expression. Users also wanted to use our vector search capabilities with this Redis Query Engine. The way to model a vector into JSON is just by using an array, and you have all the values of your vector in that array. The problem that with this initial data structure that we've created was that if you would model the same vector in a JSON data structure, it would consume 7 times more memory than it would do in a JSON, sorry, into a hash. Which makes it like very impractical because it would be way too expensive to use that. So it's great that we have this capability, but it was not useful for vector search capabilities. So what we did is we actually built a feature that allows us to compress vectors, and we call it like for homogeneous arrays. So when all the elements in your JSON are of the same type or the same element, we can actually compress that. Rather than having type, value, we'll now just like compress that. And for specific vector types, we can actually reduce the memory up to 92%. And that really makes it like practical, because before that it was like 7 times more, and now it's actually even less than hash. I think this is really interesting because now we can actually model hierarchical data in Redis and also add a vector similarity search on top of that. Now, that's not the only thing that we've been improving. We've also focused upon Redis open source and making it like incrementally faster. This is a benchmark that we did on a mixed workload, and we try to focus upon that. We try to focus upon like real-life workload, not like workloads that are like lab setups tests. So in this case, it's like 10% writes, 90% reads. We're using 4 I/O threads, but each key is 1 kilobyte in size. And every minor version that we make, there is actually an increment. And the latest version, 8.4, we actually crossed the 1 million. So on a 4-core box, right, on a single main thread, Redis process, you can now do more than 1.25 million operations. Mixed workload. And we also wanted to make it faster, of course, for our enterprise customers. So what we've done is we invested a lot in our TLS solution. So when you have like a secure connection with TLS towards our Redis cloud database, we can easily deliver 2 times the performance compared to Elasticache on the same number of vCPUs. In general, Redis 8.4, which is the latest release, is the fastest Redis ever. It's up to 40% faster in scaling up and scaling down, which is particularly important for our customers, for example, in events like Black Friday. We focus a lot upon improving the latency of each command. We can now, just by upgrading to 7.4, which was the latest, the previous minor to 8.4, you can get up to 90% latency improvements just by upgrading. I know that the top 2 there are Hyperloglock and Bitmap, which you might not be using. However, for hashes, it's up to 55%, and for sets and sorted sets, it's up to 70%. And we also added quantization into our vector search solution, which obviously drastically reduces the size of the index, but it also enables a higher throughput. And we spoke about the memory savings before. There are many more things that we did in Redis 8.4, and it would just be like a long enumeration of small things. And actually, I think they're all like paper-cut fixes. Sometimes you need to use 2 commands to, for example, to add an element into a specific key and then do an expiry, which required you to do a transaction, et cetera, et cetera. So there are small things that we keep on improving and actually make a better experience for our developers. There are many there. I don't want to go over the long list, but we wrote a long blog post about that with all those changes. And I'm happy to say that Redis 8.4 is now also GA, generally available for Redis open source, and it will be available early next year in our cloud and also for our enterprise on-premise customers. I've been talking a lot. I'm going to summarize, and I'm going to hand it over finally to Ever. Give me one moment. So the modern cache, like how this all evolved, like from let's say 10 years ago. We believe that the Redis Query Engine is now really an essential ingredient in our modern cache stack. It doesn't only solve like the hotkey problem for the sets and sorted sets, but it also powers new use cases such as RAG, semantic caching. It transforms existing use cases such as session store, but also feature store use cases. Client-side caching, of course, solves the other hotkey problem. Redis Data Integration, which is now hosted, allows you to cache data and keep it always in sync with your primary data source. It allows you for greater scalability, and it's fast the first time. And the last thing you need to know is that we're obsessed by latency. It's our fastest release now with Redis 8.4. We're the fastest secure cache, and we're also the fastest vector database on the planet. And I highlighted 3 red things, and these 3 red things are things that Eber from iFood is going to talk about. So I would welcome him to stage right now. Thank you. Good luck.
Thank you, Peter. So I want to share with you, first of all, my 3 goals here. My first goal is to share part of my journey and some applications that use Redis inside iFood. And my second goal is to connect these applications to what Peter showed you. And my third goal is to make my English clear to you. So I hope to achieve the first 2 goals with my English, right? First of all, I'm from Brazil. I work with tech for more than 20 years. Probably this shows part of my age. I'm at iFood for 5 years. I work inside a GenAI platform team, which is part of the ML platform inside iFood. And part of the examples that I will show you is inside this platform team. Before iFood, I worked with industrial automation for almost 15 years. And what connected me to the data and AI area was my master's degree in computer science. So I know, as I am, you will probably forget part of these numbers in few seconds. This is what I expect. But what I'm trying to show you here is that iFood has more than 106 million orders per month. And this is basically shows which is the amount of sessions that we have per day, which is the amount of users that are connected using iFood. iFood is known. Who here knows iFood? One, great. Who here knows, already went to Brazil? Great, great. So iFood is known to be the biggest food delivery company in Latin America, but it's also a company with a whole ecosystem. We don't deliver just food, we deliver groceries, we also have logistics services to deliver things to companies, restaurants, and other types of merchants. We have, when we think about partner establishments, we have more than 450 establishments. We are working or running inside more than 1,500 cities, different cities in Brazil. We have connected to the logistics ecosystem, we have more than 450 delivery people. We have probably more than 60 different users using monthly iFood app. And we call employees from iFood food lovers. We have more than 8,000 food lovers at this moment. And to connect to the applications that we'll show you, and this is the message that I want you to record from this slide. So we have thousands of different services running. When I say different services are microservices, softwares that are running and supporting all these numbers. We have agents, internal agents, or agents that interact with external partners running inside our infrastructure. So this is what iFood represents in Brazil. And the first application that I want to show you or connect to Redis is what we call internally as GenPlat. Basically, it's a GenAI platform which connects users and different services to GenAI models. It's basically a way to centralize the access to the models, but it also solves governance and a lot of other challenges. So the numbers of this platform is basically 1 trillion tokens per month, more than 400 million requests per month, and basically we have at this moment more than 200 different services using our platform to access GenAI models. Part of these models are inside AWS, part of these models are outside. For example, we have OpenAI, Gemini, and we also have some open source models that we trained by ourselves and are running and making GenAI inferences there internally, iFood. Besides these services numbers, we also have more than 500 different users that uses GenAI models to create code and use them to make their life easier and better. And where's Redis here? Redis is basically the system used to control the rate limiting. I think you already know that, but when we think about the GenAI model, you have limits. you have requests per minute limits, you have tokens per minute limit, and Redis is used inside this platform to guarantee consistency of this number. Oh, I'm a user or I'm a service, I'm using this specific model and I need to control this rate limit, and Redis is an excellent solution to do that. So the second example that I want to show here is the RAG that we have internally. This is basically, I know that we are in an agent moment, but a few months ago we were talking about, few months or probably 2 years ago, we're starting to talk about RAG. It's basically a solution that solves the missing context from the GenAI models. So if you're using an OpenAI model, if you're using a Google model or other provider model, you already know that it doesn't has your data there. It wasn't trained using your data. So the RAG solution basically solves this problem. It gives context to the models to answer things and to give you the answer you know, giving this context. So our internal RAG API basically is split in two important pipelines. The first pipeline is the ingestion pipeline, which given a group of documents, you split them in chunks, you store them at Redis vector store, and then this process is configurable by services or by projects there inside iFood. And then there's a second pipeline, which is the retrieval pipeline. During these two pipelines, we are using different models through Genplat API. The first type of model is the embedding model, which basically transforms the text or the content in a vector of numbers and stores inside the vector store. The second pipeline is the retrieve and answer thing. So if you receive a text, basically first you transform this text in an embedding, and then you retrieve from the vector store, which is inside Redis, the contexts that are near that text. And with this nearest context, you deliver it to the model, to the GenAI model to answer your initial question. So the third application example that I want to share with you is the feature store. I don't know if everybody knows here what's the solution or the pain that feature store solves, but it's basically delivering content to make inference. Inside iFood, before GenAI model were used, we developed a lot of classical machine learning, and part of this classical machine learning are making inferences to answer things, for example, give recommendations of dishes or other type of products to users that are connected to our application. So when these models are making inference, they need information, they need inputs, and these inputs are stored inside feature store and connected to those sessions, users, establishments, partners that I showed you. We have this type of solution. Basically, you need to make a recommendation, for example, to a user, sometimes thousands or millions of users, and you retrieve some features from that user from the feature store, and you give it to a classical machine learning model, and the output is basically a recommendation that can be used there. So with the feature store, we basically have two different types of storage solutions. One is for offline inference, which basically is inside our data lake, and the second one is stored inside Redis. So when we want low latency, when we need to deliver things to the model and make inferences below, let me see here, 10 milliseconds, we use Redis. This is basically one of the best solutions or best points that Redis solves there inside iFood. So this is it. This platform also delivers more than 5 million requests per second. And this is basically because we use Redis. And we have more than almost 2,000 different features that are available there. This is it. I think we already